So far, we have studied what the word stress means, what the word strain means, or the definition of the term stress tensor and the definition of the term strain tensor. We've also studied the Newton's equations of equilibrium in its differential form applied to a continuum. In the next set of lectures, we're going to study the constitutive behavior of linear elastic materials. And by the constitutive behavior of linear elastic materials, I mean the relationship between the stress and strain. And usually this is obtained by taking samples of your material, taking those samples to the lab, and then applying a certain force on this specimen and calculating the longitudinal stress by dividing the force by the cross-sectional area and measuring the corresponding deformation. And drawing the relationship between F over A and delta over L. Now, the relationship could have different forms. You could have a material that is that behaves in a linear way. You load it and you unload it, and the relationship is linear. You can have a nonlinear material, but still follows the same curve as you load and as you unload. And you could have different materials that as you load, you require a lot of force to increase the displacement, but when you unload, the force drops really fast and you don't need a lot of force to unload the specimen, where here there is some lost energy during loading and unloading. In this chapter, we're very interested in only the first type of material, the linear elastic materials, where the relationship between the measures of the stress and the measures of strain, the relationship is linear. But before we study this material, we're just going to go through the different types of materials and their classification. The first classification of materials is I classify the behavior of the materials according to linearity. If the relationship between the measures of stress and the measures of strain is linear, then this material is a linear material. Otherwise, it's not linear. Now, elasticity is different from linearity. Elasticity has to do with the energy dissipation. So, a material is elastic if it does not dissipate energy during loading and unloading. What does this mean? It means if this is a measure of the stress and this is the measure of strain, the same amount of effort that is needed to load the material, as you unload the material, you follow the same curve, so at every value of the strain you have the same value of stress. if a material goes up and down on the same curve, this material is elastic and does not dissipate any energy. If, on the other hand, loading and unloading are different, so I'm going to write here elastic. This is non-elastic. If the behavior is non-elastic, you might dissipate energy. So as you load, you need a lot of force to increase the displacement. When you start unloading, the force drops really fast, and then the strain starts dropping fast at a very small force, and you might even have a displacement, what we call residual displacement. Or plastic deformation. For example, you get a bar. This is the undeformed length of the bar. The force here is 0, starting at this point. Then the force is increased. For example, the force is equal to 100 Newton, and then slowly you release the force, and as you release the force, when P is equal to 0, you have some residual or plastic deformation. This is loading. And this is unloading of the material. So the formal definition of an elastic material is the following. If the material does not dissipate energy during loading and unloading, then the material is called an elastic material. Otherwise, it is non-elastic. Now notice that there's a difference between linearity and elasticity. You can have a non-linear material that's elastic. This very first curve that we draw here is an example of a material that's non-linear, still elastic. The relationship between the stress and the strain is non-linear, but the material does not dissipate any energy during loading or unloading. Traditional engineering materials, such as steel and concrete, are usually linear and elastic. So basically, the stress-strain curve of traditional materials is a linear elastic material, is just a linear line between the stress and the strain within the range of applicability of the material. Materials like rubber or other polymers you might find that the relationship between the stress and the strain is non-linear but still elastic. Usually when the material dissipates energy, this energy goes into the material in the form of some damage inside the material. You could be heating the material up and damaging some of the molecules, or you could be damaging some of the connections inside the material, such that at the end, after unloading, you have some plastic deformation, which means you have added some damage to that material. We also classify the material according to direction or material symmetries. So if I take a specimen, or if this is the material, if I take a specimen in this direction and I draw the relationship between the stress and the strain, and for example I find that it's linear with a slope of 100 units, and then I take a specimen in another direction and I draw the relationship between the stress and the strain, and I also find that it has the same slope. If I do it in any other direction, and I find the same relationship, then this material is called isotropic. An isotropic material is a material whose relationship between the stress measure and the strain measure is independent of the orientation of the specimen. It doesn't really matter what the orientation of the specimen is, you get the same relationship between the stress and the strain. If on the other hand you test it in one direction and you get 100 MPa, or you get a slope between the stress and the strain of 100 units, and then you get a specimen in a different direction and you get a relationship between the stress and the strain with a slope of 10 MPa, then the relationship depends on the direction, and then this material becomes anisotropic. So if the response depends on the orientation, the material is called anisotropic. Now there are different levels of anisotropy. The first one is called general anisotropy. That's when I cannot identify any symmetry. I cannot find any directions that kind of look like each other, or the material behaves in a very random way. You're pulling in one direction and you get shear in a different direction. So we call this a general anisotropic material, and we say that this response is not symmetric. There are materials that have three axes of symmetry, the three axes of symmetry, and we call these orthotropic materials. Orthotropic materials are a special kind of anisotropic materials in which there are three perpendicular axes of symmetry the response is symmetric along those three axes of symmetry. When we say the material response is symmetric, we mean that along this direction, if this is one of the axes, along this direction, when I pull and when I draw a plane perpendicular to this axis of symmetry, the response of the material on this direction is the same as the response on this direction, which basically means that there's no shear. When I pull along the direction of the axis of symmetry, no shear deformation occurs. So examples of this materials are materials that have some sort of fibers oriented in three directions. You can get a polymer material which has fibers in this direction that gives it a certain behavior in this direction, and fibers in a different direction that gives it different stiffness in the third direction, and these fibers might not be the same, so you get different Young's modulus in each direction, and perhaps no fibers in the third direction. So in the third direction you get a totally different Young's modulus or totally different stiffness, and the behavior is symmetric around those three axes, along those three axes of symmetry. The third type of anisotropic material is called transversely isotropic materials. So we've got general anisotropic materials, orthotropic materials, and then we have transversely isotropic materials. Transversely isotropic materials are those that have an axis of symmetry where there is a certain stiffness for this material. For example, it has fibers along a certain direction, so the response in this direction is or there is a certain value for the response, or there's a certain value for the stiffness along a certain direction, but any direction perpendicular to that, the response is the same. So I call this plane of isotropy, which means perpendicular to the, and this is an axis of symmetry, and there's a plane of isotropy. If I take any specimen in that plane of isotropy, the response is the same. Example, wood, which has fibers oriented in one direction. Wood is a very good example of isotropic material, transversely isotropic material. So transversely isotropic materials are materials that have one axis of symmetry perpendicular to a plane of isotropy. So we can also classify materials according to homogeneity. If you find a block of material and you want to test whether this material is homogeneous or not, homogeneity means it's all made out of almost the same material. So in a homogeneous material, the response is independent of the location within a specimen. For example, if I test this area, I get a certain response. If I pick my specimen from a different area, I get the same response. If I test my specimen in this area, I get the same response. Or if I test in a different area, I get the same response. In general, materials, however you make them, are not purely homogeneous, because when you test any specimen in the lab, you get a response. So let's say this is specimen number 1. You take specimen number 2, you get a slightly different response. Specimen number 3, you get slightly different response. But we can group, if this response is very close to each other, we group this and we assume that the material is still homogeneous. And of course, most of our engineering materials, even though they might be made of non-homogeneous constituents, we still, in most cases, assume that they are homogeneous. For example, concrete. So, concrete can be non-homogeneous in nature because a concrete specimen might have different type of aggregate, different type of material, different type of cement. So if you pick your specimen, a small specimen close to the aggregate, you might get a very strong response or very stiff response. Maybe in the cement area you might not get the same response. But in general, because our specimens are usually large enough to include all the different constituents, we still consider that the behavior, practically speaking, is homogeneous. So even though concrete can be non-homogeneous in nature, yet it can be considered homogeneous because average specimens behave the same. Now, if you get some concrete and you put some steel in it, some steel bars, now this is non-homogeneous material. Specimen from here does not have any steel bars. It has a certain response. A specimen from here containing steel bars have a different response. We also classify materials according to time dependence. So in general, if you take a specimen to the lab and you pull it in a certain direction and you measure the response in another direction, the response or the response will depend on how fast you actually pull the material. The faster you pull the material, the faster you're doing the experiment, you will actually see a more a stiffer response. The faster you pull the material, the stiffer the response. Now that means that the material, it really depends on the time. It's time dependent. So depending on of course how fast you're pulling the material, and depends on the range of applicability of this material, if I can group all these time dependent responses together, so for example if the time dependence is very small, then I can assume that this material is not time dependent. So a material whose response is dependent on time is called viscous material. Otherwise, or also it's called rate dependent. Otherwise, the material is non-viscous or non-rate dependent. Or maybe rate independent materials. Now, other forms of rate dependency or viscous materials is what we call stress relaxation and creep. And stress and relaxation and creep are very important phenomena for the design of both steel and concrete structures, because creep is a phenomenon that occurs in concrete quite a lot, and stress relaxation is a phenomenon that occurs in steel, especially pre-tensioning cables. So what is creep? So let's say you have a concrete bar and you hang a load from this concrete bar. So this is day 1. This load is fixed, M. You come the next day and you see that slowly the bar is creeping, you come a third day, or you come on the third day, you see that the bar has even creeped further. So creep is the increase in deformation over time under constant load. And it's a problem in concrete structures, because if you actually go to an old concrete building, you're gonna and you walk on the slab, you're gonna find that the slab has actually creeped and it's sagged in the middle. So designers of concrete buildings usually take creep into consideration. Stress relaxation is a different form of stress relaxation is a different form of time-dependent response. You have a steel bar, and you pull this steel bar with a certain deformation, and then you put a timer and measure the force. So this deformation is constant, and then day 1 you measure the force. Then the second day you measure the force, and the force has decreased even though you haven't moved your bar. Day 3 you measure the force, and it's even decreased further. So this decrease in the force under constant deformation over time is called stress relaxation. So stress relaxation is the decrease in stress or force over time under the application of constant deformation. And this is an important problem when you're designing a pre-stressed concrete beam, because a pre-stressed concrete beam, you take a bar and you apply a certain stress to this bar, and this stress is used to push against this concrete beam, to apply a pre-stress on this concrete beam. And so you want to make sure that 5 days or 10 days or 100 days from now, the force that you designed this concrete beam on is still there, or you want to consider that this force might decrease, and so you need to understand the behavior of the steel due to stress relaxation. So these are very interesting, and there's a lot of research in all these kinds of materials. But the one material that we're going to be studying for the rest of the course is the linear elastic material, the most simple material of all these materials. So linearity means the following: that if variable y is related linearly to variable x, that means y is equal to a constant multiplied by x. So this is a linear relationship between y and x. Now, what we studied is that stress is a matrix, and the strain is a matrix. When we say that there is a relationship between the components of the stress and the components of the strain, we mean the following. We mean that sigma on 1 is a linear function of these components. So constant 1 multiplied by epsilon 1. And this constant, I will call it C. But because I will have so many constants, I'm going to take 1, 1 and put it here. And this 1, 1 and put it here. So this is the constant number 1, 1, 1, 1 that relates sigma on 1 with epsilon 1, 1. And then I have epsilon 1, 2. It's multiplied by a different constant. This constant relates 1, 1 with 1, 2. And so on. Which is basically C 1, 1 ij epsilon ij summed over ij equal 1 to 3. Or you could say, I'm just going to use a different variables, KL 1 to 3, C 1, 1 KL, epsilon KL. Or I could possibly say that sigma ij, for any value for I and j, this is equal to the sum C, the constant that relates the component Cij, to the component KL, epsilon KL, and the sum is over KL equal 1, 2, 3. And when we calculate those, how many constants we have, because we have 9 components of stress, that have to be related to 9 components of strain. You have 9 by 9, 81 constants. In general, I'm expecting 81 constants. And these constants will look like the following table. Sigma on 1 is a function of all the strain constants. So sigma on 1 is equal to C1111 multiplied by epsilon 1 plus C1112 multiplied by epsilon 12 plus C1113 multiplied by epsilon 13, and so on. So these constants relate sigma on 1 to all epsilon ij's. These relate sigma 1, 2 to all epsilon ij's. And so on. So in general, I'm expecting 81 constants. However, we studied that sigma 1, 2 is equal to sigma 2, 1. So we said that the stress is symmetric. Not only this, we also said that epsilon 1, 2 is equal to epsilon 2, 1. So we said that the strain is symmetric. So what does this mean? It means the following, that since sigma 1, 2 is equal to sigma 2, 1, that means any constant that has 1, 2 ij has to equal to sigma 2, 1. Sorry, has to be equal to. So since sigma 1, 2 is equal to sigma 2, 1, that means any constant that has 1, 2 in it, and then ij, has to be equal to the constant that has 2, 1 in it, multiplied by ij, which results in that sigma 1, 2 has to be equal to sigma 2, 1. Which means that sigma ij kl has to be equal to sigma ji kl. So the first two, if you swap them, you get the same constant. And since epsilon 1, 2 is equal to epsilon 2, 1, swapping the second, the last two components also should give me the same constant. So because of the symmetry of both the stress and the strain tensors, we are able to simplify the relationship between the stress and the strain only for the sake of ease of notation, instead of using this huge matrix of 81 components which already have equal values, because we already know that C1211 has to be equal to C211 and C32, for example, 23 has to be equal to C3232. Then we can replace this relationship with a simplified version only for the sake of the constitutive relationship by viewing the stress as a vector of 6 components: sigma 1, sigma 2, sigma 3, sigma 1, 2, sigma 1, 3, and sigma 2, 3, and the strain as 6 components, and we're only left with the components, the independent components that we have. So now you can see that you have C1112, but you don't have C1121 because we already know that they're equal. So by adopting this convention, we have now 36 constants which are independent. And this is after considering that the stress and the strain are symmetric. Now, this is a problem that I always ask in the final exams and in the midterms. This matrix, which is a 6 by 6 matrix, is not necessarily symmetric. We never mentioned that this has to be equal to that. So far, these are not equal. However, due to energy considerations, and as we are going to cover right now, due to energy considerations, this value has to be equal to this value. So due to energy consideration, the matrix containing, or the matrix representation relating the vector of sigma with the vector representation of epsilon has to be symmetric. It has to be symmetric only for energy considerations. Without going into too much details, but for this material to be elastic, that means the following. Since loading and unloading, I'm always following the same curve, then sigma in this case is equal to what I call a strain energy, which we will cover closer to the end of the course, but it's the partial derivative of this strain energy, or the energy that's stored inside the material, with respect to the corresponding strain. And this means the following. For example, sigma on 1 is equal to partial u by partial epsilon on 1, which is equal to C111 epsilon 11 plus C1112 epsilon 12 plus, and so on. So, partial sigma on 1 by partial epsilon 2 is equal to the following. Partial the above which is equal to C 1 1 1 2. But because we assumed that this U exists because it's an elastic material, this is equal to partial by partial epsilon 1 1, and I'm going to replace partial epsilon 1 1 with partial epsilon 1 2 2, which will happen to be equal to C 2 2 1 1, which means if I swap these two with these two, I get the same constant. Swapping these two means, if you look at the matrix representation, 1 1 2 2, if I replace it with 2 2 1 1, I should get the same number. 1 1 3 3, swap it with 3 3 1 1, I should get the same number, which ends up giving me that for a general linear elastic material, we have 21 constants. 21 independent constants. And I'm sure that this material does not dissipate energy, and the relationship between the stress and the strain is linear. So all I need to do is take that material to the lab, carry 21 different experiments to find 21 different constants. I need 21 constants to fully describe this material. This is not covered in our course, in the undergraduate course. However, if the material is orthotropic, what does it mean that it's orthotropic? It means the following. It means if this is an axis of orthotropy, if this is an axis of orthotropy, as I pull here, I don't get any shear. So as I pull in sigma on 1, I don't get any shear. So you get zeros. So the relationship between the stress and the strain for orthotropic linear elastic materials, when the axes of orthotropy are 1, 2, and 3, is described by this matrix that has only, let's count the constants, 1, 2, 3, 4, 5, 6, 7, 8, 9, only 9 constants. And these constants are usually given using those some physical constants that we're used to, which are Young's modulus 1, 1, Young's modulus 2, 2, Young's modulus 3, 3. So for example, the inverse of that relationship is given as follows. The strain in the direction 1, 1 is equal to the stress in the direction 1, 1 divided by its corresponding Young's modulus. Remember, you have 3 different Young's moduli because this is an orthotropic material. Epsilon 1, 1 is affected by sigma 2, 2 divided by E 2, 2 using a certain Poisson's ratio. It's also affected by sigma 3, 3 divided by E 3, 3 using a certain Poisson's ratio. It's not affected by the shear stress in any of the third directions. If I have shear stress, I don't get any longitudinal strain. And so on. You get this relationship between the strain and the stress. And because we said the material, because material doesn't dissipate energy, the matrix has to be symmetric. This matrix has to be symmetric, so this value has to be equal to this value. And so the 9 constants that I need to calculate in the lab are G23, the shear modulus that relates to the shear the shear strain with the shear stress in this plane, epsilon 1,3 with sigma 1,3. I need to calculate the shear modulus, so 3 different shear moduli, 3 different Young moduli, and 3 different Poisson's ratio. 3 different Poisson's ratios, 3 different Young's moduli, and 3 different shear moduli will fully describe this material for me. The next type of material, the transversely isotropic elastic material. So, for this material, given that E3, let's make this as E3. This is the axis of orthotropy. Sorry, axis of symmetry. And this is E1 and E2. This is plane of isotropy. When this is the case, then the relationship between the stress and the strain will be described by 5 constants. Those constants are 1, 2, 3, 4, and 5. So I'm going to have to take this material to the lab. If I know that it's already transversely isotropic material, I have to do 5 different experiments to find 5 different constants. 1 for shear, 1 for Young's modulus in a certain direction, and 1 for a different Young's modulus, and so on. So 5 different experiments to find those 5 different constants, and those 5 different constants can be given as follows. One Young's modulus in the plane of isotropy, the Young's modulus in the different direction, G13, so E33 in the third direction, G13, which is the shear modulus that relates the shear deformation in the plane made out of E1 and E3, and also E2 and E3, because E1 and E2, that direction is because there's isotropy in 1 and 2, so G13 is equal to G23, and that's why we only need to calculate one of them. We also need the Poisson's ratio in the plane of isotropy, and the Poisson's ratio that relates the plane of isotropy with the other plane. So now we have 1, 2, 3, 4, 5. And in the plane of isotropy, G is equal to E divided by 2, 1 plus Poisson's ratio. So we need 5 independent constants to describe the material. For isotropic linear elastic materials, as we already know, we need 2 independent constants. Those 2 constants are E and Poisson's ratio. G, as we know, is dependent on both because it's equal to E divided by 2, 1 plus Poisson's ratio. And this is the relationship between the strain and the stress is given by this matrix. If you invert this matrix, sometimes I'm interested, I know the strain and I want the stress, or I know the stress and I need the strain, and this is the inverse. Given the strain, I can find the stress. Here, given the stress, I can find the strain. So far, we have shown that in a linear elastic material, isotropic linear elastic material, I have two independent constants, E and Poisson's ratio, but G is related to those. And I would like to show you now how I would prove, or how I would show, that indeed G is given by E divided by 2 multiplied by 1 plus Poisson's ratio. And to do this, we're going to utilize the elements of linear algebra that we've been studying so far from the beginning of the course. So, starting from a state of pure shear, we need to show that the shear modulus is equal to Young's modulus divided by 2, 1 plus Poisson's ratio for a linear elastic isotropic material. So given that the stress is equal to 0, sigma 1, 2, sigma 1, 2, 0, the vector representation of the stress, just for the ease of utilizing the relationship above, looks like this. From the relationship between the stress and the strain, looking at this relationship between the stress and the strain, I know that this is 0, 0, 0, sigma 1, 2, 0, 0. I have the only non-zero component in the strain will be the 2 epsilon 1, 2. Everything will be equal to 0 except sigma 1, 2, because everything else is zeros. From this relationship, therefore, 2 epsilon 1, 2 is equal to sigma 1, 2 over G. Which means that the strain matrix 0. Now notice that in the above relationships I use the traditional shear strain, which is double the shear strain that I'm using in the matrix. So this is equal to sigma 1, 2 divided by 2G. Alright, now I'm going to use this relationship, but now in a different coordinate system. I'm going to use a different coordinate system that's oriented 45 degrees with the current coordinate system. So in the current coordinate system, I have shear, and I have E1, E2, and E3. Now I'm going to use a new coordinate system. Where Q, this is oriented 45 degrees, and E-3 is equal to E3. And so for this, Q will be equal to 1 over root 2, 1 over root 2, 0, negative 1 over root 2, 1 over root 2, 0. I would like to find my new stress matrix, which is equal to Q sigma Q transpose. The new stress matrix will look like this. In this new coordinate system, I'm going to have different representation, and it will look like this: sigma 1, 2, 0, 0. Which is equal to sigma prime, the new sigma prime 1, 1, the new sigma prime 2, 2, and they're related to the old components, which were sigma 1, 2 and sigma 1, 2. Similarly, the new strain in the new coordinate system is equal to Q Q epsilon Q transpose, which will be equal to epsilon 1 2 negative epsilon 1 2 0 0 0 0 0, which is basically equal to the new component epsilon prime 1 1 and epsilon prime 2 2, and the rest are zeros. Now in the new coordinate system, since the material is linear isotropic, I know that in the new coordinate system the relationship does not change. And so epsilon prime 1 1 is equal to sigma prime 1 1 divided by E minus Poisson's ratio sigma prime 2 2 divided by E minus Poisson's ratio sigma prime 3 3 over E, and this is actually 0 because sigma prime 3 3 is 0. But I know that the new epsilon prime 1 1 is equal to epsilon 1 2, which in fact is equal to sigma 1 2 over 2g from the relationship in the earlier coordinate system. Sigma prime 1 1 is in fact equal to sigma 1 2. Sigma prime 2 2 is in fact equal to negative sigma 1 2. From here you're going to find that 1 over 2g is equal to 1 plus Poisson's ratio divided by E, from which you obtain that g is equal to E divided by 2 1 plus Poisson's ratio. So basically what we said, or what we did here, is the following. We have a certain coordinate system. We have a relationship between sigma 1 2, sigma 1 2, epsilon 1 2, and epsilon 1 2, from which we know that sigma 1 2 and epsilon 1 2 are related with G. But because we can find a coordinate system in which the stress does not have shear and the strain does not have any shear components for this particular problem, I have, so this is sigma prime, this is epsilon prime, I have a new relationship between sigma prime and epsilon prime, utilizing only Poisson's ratio and nu because we don't have any shear. And by relating these two stresses together and these two strains together using the matrix functions that we learned in linear algebra, we can relate E nu and G. So the last thing that we are going to talk about for this part is alternative material constants. So we are used to, from our initial or introductory strength of material courses, you have learned that the relationship between the stress and the strain is given by the two material constants E and Poisson's ratio. There is no way, or there's no reason, that these are the only material constants that you can use. But there are other material constants that are functions of E and Poisson's ratio. For example, G, which is equal to E divided by 2, 1 plus Poisson's ratio. And the relationship between the stress and the strain can be function of any of the two constants, any two of the following constants. So it could be E and Poisson's ratio, it could be E and G, it could be G and Poisson's ratio, or it could be the bulk modulus K, which is equal to E divided 3, 1 minus 2 Poisson's ratio. And the bulk modulus is the relationship, or the constant of proportionality between sigma 1 plus sigma 2 plus sigma 3 over 3, which, if you remember, that's the hydrostatic stress, and epsilon 1 plus epsilon 2 plus epsilon 3, which is, if you remember from the definition of the strain, the volumetric strain. The relationship between the sum of those three and the sum of those three are related using a constant that's equal to E divided by 3, 1 minus 2 Poisson's ratio. There are two other constants that you might find at some point in your life. You might come across. They're called Lemay's constant, and Lemay just used to be a person who studied the stress and the strain and found that if he replaced E multiplied by Poisson's ratio divided by 1 plus Poisson's ratio, 1 minus 2 Poisson's ratio, he could represent the relationship between the stress and the strain in a simpler way. And you can check the exercises at the end of this chapter to see why Lemay used these constants. A note on Poisson's ratio. We are going to study in the next part that Poisson's ratio can never, for linear elastic materials, can never be higher than 0.5. Basically, Poisson's ratio is always less than 0.5. And what does this mean? It means that epsilon 1 plus epsilon 2 plus epsilon 3 under this constant state of stress, so I have sigma 1 only. This is the volumetric strain, when I can use the small strain to describe my material. Epsilon 1 plus epsilon 2 plus epsilon 3, given the relationship above, will be equal to sigma 1 over E minus Poisson's ratio sigma 1 over E minus Poisson's ratio sigma 1 over E, which is equal to 1 minus 2 Poisson's ratio over E multiplied by sigma 1. Since Poisson's ratio is less than 0.5, therefore 1 minus 2 Poisson's ratio is always greater than 0. Therefore, epsilon 1 plus epsilon 2 plus epsilon 3 is always positive when sigma 1 is positive. Which means for a linear elastic material, linear elastic isotropic material, when when you stretch the material, the volume always increases. Always increases. Now, one of your assignment problems asks, what does it mean? That that Poisson's ratio is equal to is positive, and what does it mean that Poisson's ratio is negative? And so Poisson's ratio is negative means as you pull, rather than the material contracting in the third direction, it actually expands. And you should Google materials that expand laterally upon pulling. You will find very neat materials that are made out of very special polymers, such that as you pull the material, it has a negative Poisson's ratio, which means as you pull the material, it expands laterally. Now, remember that for any linear elastic material, you are still expecting the material to increase in volume as you expand, or as you pull in a certain direction. So the material always increases in volume. So in the next part, we're going to study some restrictions on the relationship between the stress and the strain. Then we're going to study the plane, or the plane stress and plane strain, and then we're going to go through different problems that relate the stress to the strain.